Great. And for those who are staying, we've got some great experts here to share some of their insights on working on some really innovative projects. So I'll let people transition. And in the meantime, I'll share briefly my screen here, which lays out our session 3B. So hopefully people can see that. And really, it's just a placeholder because I've got one more slide, and then I'm going to pass it off to Michael. And Michael, hopefully you're prepared to share your screen. Good to see you. But we've got three speakers lined up for this session, and my hope is that you'll not only get to hear about kind of the technologies that they've been working on and their experiences, but then we'll be able to get into a discussion about some of the what they can share, some of their best practices in working through it. So without further ado, I think folks have had enough time to transition if they want to the other session. Let's go ahead and get started with Michael Siminovitch, professor in design and also the director at the California Lighting Technology Center. And Michael, you probably will say this, but you are also the Art Rosenfeld Endowed Chair in Energy Efficiency, which is wonderful. Michael?
Great. Thank you so much, Ben, for the introduction, and welcome everybody to this afternoon's program. Really looking forward to the other talks as well. So thank you. And so you can all see my screen?
I can't see your screen. I'll stop sharing mine, but do you want to try hitting that share button?
Yeah, it says screen sharing.
We can see it, Michael, but you might want to hit presentation mode.
Okay. How's that?
Yep, that works.
Good. So I'll get right into it. This is some work that I've been doing over the last couple of years now. I've been partnering with Professor Christopher Zachary, who is chair of the dermatology department at UC Irvine, and also Mazi Sharak, long-term Energy Commission lead engineer. And this has to do with the application of a unique UVA IR filtering protection for vehicles in the state of California as a statewide initiative. And so I'm just going to get right into it. UV is a very strong carcinogen for humans, and there's a particular strong threat relative to vehicle exposure. There's quite a significant skin cancer risk from driver's side window exposure in standard passenger cars, contractor vehicles, buses, police cars, etc., and many of the common vehicles that we have in our colleges and campuses. And so the three of us dug into this issue, and there's a statistically significant laterality associated with left side skin cancer relative to driver exposure. So if you look at standard non-melanoma cancers, about 74% of basal cell cancers are on the left side of the face. If you look at melanoma, the really dangerous one, there's a smaller laterality issue, but it's still statistically significant, 53% left side. And so we partnered with the dermatology department at UC Irvine and one of the leading experts on skin cancer, and we have some quite good research on this issue. And there's a number of follow-up references which are more than welcome to look at. But in round numbers, approximately 1 in 100 skin cancers is due to driver exposure. And this is typically the basal cell cancers. The melanoma, it's like 1 in 130. Still, that's a large number when you look at this on a statewide basis or even at a university basis. And we found that, within the police departments and contractors and people who largely drive for a living, this is known and understood as an issue. So we did a lot of measurements, a lot of research on this. And it turns out that front windshields of all cars in the United States are laminated glass, and it does an excellent job of screening out the UVA and the infrared. Unfortunately, the driver's side, about 80% of all vehicles in the state of California are tempered glass and largely transmit the UVA. And this is where the threat comes from. And basically tempered glass and laminated glass. We did a lot of measurements, and what I'm showing here, the blue bars here is the relative amount of UVA coming through the front windshield. And so across the United States, all vehicles approximately the same, very little UVA getting through the front windshield. But driver's side, not true. But 80% of the vehicles, it's letting in the UVA. What was interesting was there are about 20% of commercial vehicles sold in the state of California that have a laminated glass on the driver's side, which do an excellent job of limiting this. But unfortunately, this is not ubiquitous. It's not applied evenly. So the proposed solution here was that was to introduce a statewide requirement that would require UVA filtering on all vehicles sold in the state of California. And so this is a proposal that we're trying to advance. This is actually simple and it's low cost. It's being done today in 20% of the vehicles without any commercial implications. Relative to the kinds of applications we're thinking about for universities and colleges, it can be easily retrofitted into vehicles. Relatively simple retrofit completely eliminates the UVA largely. But what's also very interesting is it also limits the infrared component. And the infrared component is quite important relative to vehicle savings, air conditioning. And so air conditioning is a really significant issue relative to vehicle efficiency. And if we limit the infrared component here, we can actually get quite a large savings on this. So we looked at this in detail. We did a lot of state projections. And if we implemented this on a statewide basis, it would be equivalent to almost half of the 2022 building efficiency standards, which makes this one of the largest energy efficiency projects that we've ever had. So we're really looking at this as a big opportunity for carbon reduction, vehicle efficiency enhancements. And we think this is a really significant opportunity for campuses and colleges. And so, we just did some simple projections on this, but basically, 10 to 30 gallons of gasoline, can be saved on this per year, just with the simple implementation of UV-IR filtering. Whoop, let me go back. So we made a recommendation to our Energy Efficiency Institute board as sort of a broad recommendation to all of our partners. One is we should commit to fleet retrofits. And this is something that colleges, universities, utilities all own and operate large fleets of vehicles. We have a lot of police vehicles, contractor vehicles, school buses, general maintenance vehicles. And so we should be retrofitting our vehicles now for both a health and safety and also an energy efficiency. We also said we purchase a lot of vehicles and adopt the Davis spec for future purchases. There's no cost implications on this. All the manufacturers currently manufacture some cars with laminated glass. So this can be easily done, a simple decision, which would give us the vehicle savings plus the added safety benefits. Retrofitting window film is a relatively simple process that can be done on our existing fleets. And this kind of film, if you look at the comparison of glass versus these films, can completely reduce the UVA component. Just as at the same time, I could completely eliminate the infrared component largely. What's interesting is EVs are already doing this. And the reason they're doing this is they need the added vehicle efficiency in order to extend their mileage. So we should be applying the same level of good thinking to our existing fleets and our internal combustion engine vehicles, which we own a lot of. So I'm going to close on this slide. And basically, I would ask the group to consider committing to fleet retrofits and adopting our spec for vehicles. And I would leave this, turn this back to Ben Finkelor. Thank you.
Thank you, Michael. I think we can pause if there's any kind of technical questions. We'll get into a discussion shortly after, but if there's any technical questions, feel free to put it in the Q&A. or in the chat. I'm not seeing any offhand right now, so you can obviously come back to those as well in the future here. So let's go ahead and pass it over to our next speaker, Theresa. I don't see you on camera yet, but I assume you're still here. Here you are.
I'm
Would
here.
you like to?
Yeah, sorry,
Great.
I thought I was the third speaker, but I can be the second
Oh,
speaker.
okay.
I'm ready to go. I'm ready to go.
Okay,
Here
go
we go.
for it. All right.
All
Thanks,
right.
Theresa.
I will be ready to go very quickly. Hold on. Okay. All right. So I want to share with you two topics today that I thought were both important to facility management. And the first one is talking about how to think about leaks in HVAC systems that we attribute to Schrader valves. And so a Schrader valve is a service access port for adding or removing refrigerant from an HVAC system. And essentially what they do is when you connect your refrigerant hose, it pushes down this pin, which opens up a valve here, and the refrigerant can flow in and out. There are basically two gaskets in the system. One is here where the piston is, and the second one is here where the valve sits into the body. So here's a cutaway view. You can see the first gasket here, and the second gasket is down here. I just want to briefly recognize those that contributed to this project and our research sponsor, the Natural Resources Defense Council, or NRDC. So how did we get here? We were contracted to do a study on refrigerant leaks in packaged HVAC systems. And so we went out to a school district a number of years ago in 2020 and 2021, and we analyzed the refrigerant use at that school district in 1,800 pieces of equipment. So we basically went through all the refrigerant purchases, and we went and looked at all of their HVAC inventory, and we calculated the leak rate as a percentage of the total refrigerant on site. And we came up with about 3% for R22 and less than 1% for R410A. The big difference between those two pieces of equipment is that the R22 equipment is obviously older because of the refrigerant phase out. We then did an analysis of all the service tickets associated at that district, basically when someone calls and makes a complaint and a technician then is dispatched. And the technicians cited the service port or the Schrader valve as the most likely leak source. And if you're interested, this is published in ASHRAE Journal, and it's not freely available, but if you're not an ASHRAE member and you send me an email, I can send you a copy. So then we started to want to know a little bit more about Schrader valves. And so we went to an HVAC recycling yard and we recovered 60 used Schrader valves. That was an interesting phone call. Hey, can I come to your recycling yard and harvest your Schrader valves? And then we came up with a leak test mechanism. So basically what we did here is we made this valve body and we put pressurized nitrogen in this tube here. Here we're monitoring the pressure in the tube, and then we put the Schrader valve. So basically, if the valve is not leaking, you would expect that the pressure would remain constant over time. But if the valve is leaking, you lose the nitrogen and your pressure decreases. This is a very small volume of nitrogen so that we can detect the leak fairly quickly. Here's an example here on the bottom corner of a leaking valve. And so you can see how we lose nitrogen over a couple of days. So we then basically calculate our leak rates of the nitrogen, and then although it's not a perfect, it's a little bit of an approximation, we estimate what that would mean in terms of lost refrigerant, in terms of refrigerant gas. Here's just a quick picture of our valve harvesting and the valves we picked up. Notice, obviously, this equipment is at end of life. We don't really know how old this equipment is or how old these valves are, but this essentially, in my mind, is like kind of a worst case scenario. The valves might leak more than you might find on the roof because this is equipment that's been essentially at the end of its life at this point. So what we found is that we tested 61 valves, and 8 of them, or 13%, was leaking. Of those that were leaking, the leak rates here in terms of grams per year, the distribution is quite large in terms of how fast the valves were leaking. So for example, this one that was leaking at 9 kilograms per year, that one, as soon as we put that valve in, we could just hear it. The rest of them, not obvious. Some of these larger ones were detectable. We could do like a soap bubble test and we could see the valve leaking. But then we tested, we actually took out the valve body and we just tested gasketed caps. So in a worst case scenario where your valve is leaking, the gasketed cap completely stops the leak. And so the big takeaway here is that valves do leak, and we have attempted to quantify that. The leaks, the implications of the leak is that we're releasing refrigerant to the atmosphere, which is a greenhouse gas. We're also reducing system cooling efficiency or heating efficiency if it's a heat pump. And so my message to you today is to make sure you have good gasketed caps on all of your packaged HVAC systems. It's really cheap and you're going to gain something there. And I just have a link here to the publication that describes the leak testing work if you're interested. Oh, and here's some pictures.
Can you copy that into the chat, Theresa?
I will when I'm done presenting,
maybe,
so I don't have to multitask. So during the third presentation, I'll put them there. Just here's some pictures, just so you can see. Here on the left, here's what a brand new, nice new valve looks like. And here's some of the ones that have been used over the year, or that we pulled from the used valves. So you can see that the valve kind of gets an impression here and gets hard. And sometimes big chunks rip off here. And this one's just completely gone, the gasket material. Okay, switching gears completely. The other thing I wanted to tell you about today was low-cost retrofit of ventilation and filtration systems to improve indoor air quality and energy efficiency in buildings. And I just want to acknowledge our contributors, and in particular our sponsors, Flu Lab and the California Energy Commission. And so what this project is about is thinking about how we control the ventilation rate in a packaged HVAC system. And then the simplest implementation, the ventilation rate will be fixed. Essentially, this damper is in some fixed position. So when the return air mixes with the outdoor air and then goes to the supply air, we'll have essentially a constant outdoor air fraction. A very common technology in California is an economizer. So basically what that does is when the outside air is cold and we call for cooling in the building, we increase outdoor air to like 100% of the supply airflow rate, and we cool the building essentially for free cooling. And the final technology is demand control ventilation, where we monitor indoor carbon dioxide concentration as we're all exhaling. We're creating carbon dioxide. The control system is working to maintain CO2 at a set point, and it adjusts the damper. It attempts to adjust the damper accordingly to have like a steady state CO2 concentration. And then finally, we can combine economizer and DCV so that we're running DCV, and then when we need free cooling, the economizer will override the DCV and bring in 100% outside air. The really big problem with this strategy is it doesn't consider the implications of outside air pollution. So on a cold winter morning, when there's an inversion or there's wildfire smoke present, those outdoor air dampers will all open all the way and bring a bunch of pollution into the building. And facility managers that have some central controls may be able to temporarily, manually override those things. But, essentially, there's got to be a better way, right? And so this is my proposed better way, which I've called the IAQ energy controller. Like economizers and DCV was all developed as an energy saving tool, but now we want to think about both energy and indoor air quality. And so the inputs to this system are the outdoor PM 2.5 levels, the indoor carbon dioxide, and you need the outdoor temperature and the thermostat information, which you would already have in a basic control system. And we're going to output a damper position. And because we're also thinking about health, we also are going to operate a portable air cleaner in the classroom so that we're, using this entire system, the central system and the portable air cleaner together to meet some target air cleaning rates. And so the way that this works is it's built it starts with a demand control ventilation algorithm that maintains a CO2 set point. It adds an economizer. It also adds ventilative cooling. So meaning when outdoor air quality is good and temperatures are within a certain range, we're going to ventilate 100%, which is kind of like opening all the windows. And we can actually get more outside air without impacting energy savings than we would otherwise. And then finally, it's going to consider outdoor air quality. And when outdoor air quality is poor, what's going to happen is it's going to raise the CO2 set point that's operating on the demand control ventilation piece. And then a portable air cleaner is going to change speeds so that the combined ventilation and filtration from the central system and the portable air cleaner is maintaining a minimum air changes per hour for removing respiratory aerosols that we're all breathing that meets the ASHRAE 241 standard for control of infectious aerosols. And so this is the details of how it works. The goal here is for this to be just like widely available so people can just implement it without, there's no proprietary algorithms here. Basically, the first thing it does is it checks if the PM 2.5 is essentially really high. So in this case, we're saying that's over 35 micrograms per meter cubed, which is considered moderate by that's the unhealthy standard by the EPA. And if it does that, it's going to raise the set point to 1,700 parts per million. When that happens, the ventilation rate, outdoor air drops, and so the portable air cleaner has to speed up. If we're below 35, we check to see if we're above 12. That's the moderate air quality rating by the EPA. At least it used to be. Anyway, that's a long story. If it does that, we're going to just stay at 1,000 parts per million, which is a standard CO2 level, but we're not going to allow an economizer or anything like that to run. If we're below 12, we now enable the possibility to do ventilative cooling. We enable an economizer. If our outdoor temperatures are not in range for an economizer or ventilative cooling, we just run in a default mode and stay at 1,000 parts per million and kind of operate like business as usual. How the impact of this technology depends a lot on the type of filtration you're using, because we're recirculating a large portion of our air anytime we're not in an economizer or ventilative cooling mode. So I just wanted to remind everybody or point out, if you're not aware, MERV 13 filters are pretty common today, and they're available with low filtration resistance. And so with a MERV 13 filter in this hardest to remove particle range, we can remove about half of the particles on every single pass, whereas with MERV 8, we can't remove any. And I'm going to show you at the end here a difference between sort of what happens in building if you have MERV 8 or you have MERV 13. But the absolute, if you do anything in your buildings, the best thing you can possibly do is get MERV 13 filters in there, because it's just a win-win-win. And most systems can essentially work with them. There's a lot of information here, but I essentially want to make one important point that so what I'm doing here is I'm running models for 13 cities across the United States to look at the impact of this control system. And what ends up happening is we design HVAC systems based on their cooling capacity. So for example, if we're in Miami, we have much higher supply flow rates out of our central HVAC systems than we would if we're in like San Francisco or Seattle, where the weather is more mild. And so essentially the answers change depending on where you are geographically. And so that what I'm doing is I'm building a model here. And so the amount of, say, this over here is like the portable air cleaner capacity that we need. And so that goes up depending on how big our central HVAC. If our central HVAC system gets smaller, we need more portable air cleaner capacity to make up that difference. Won't go into too many details here, but essentially I built a model in order to model our PM 2.5 exposure and energy. we have to have PM 2.5 data and weather data. And in order to model that, I basically went back and I got 5 years of weather data and 5 years of PM 2.5 data for these 14 cities that I simulated. And then I basically look at a fixed ventilation control logic, an economizer, a DCV logic, and then the IAQ energy controller. And at the end, we're looking at HVAC energy, how much HVAC energy is consumed according to the model, the PM 2.5 exposure for those people inside, and the effective air changes per hour for respiratory aerosol removal. And I don't think I've stated it, but I'm looking at a classroom environment in these scenarios because classrooms are essentially one of the biggest challenges because of all those densely occupied bodies we have there. Also, children are very sensitive to PM 2.5 exposure. Okay, so here's some results for all of the cities I simulated. The top chart is basically how frequently do we get economizer cooling over the course of a school year in the different cities. So this checks out how you would expect, like San Francisco, Los Angeles, Las Vegas, Phoenix. These are all dry climates that have a lot of access to cooling in the early mornings. And so you can see these are our big, essentially, cities with economizers. Down here, we have the IAQ energy controller, and the red and the orange are the cases where the PM 2.5 was high or moderate. And so we're avoiding bringing in any excess ventilation, right? And you can see, as you would expect, like certain cities have higher outdoor PM 2.5, like for example, Stockton being, essentially the area, the Central Valley, California Central Valley being one of the biggest issues. And then you can see the blue is the ventilative cooling mode, which is we just essentially open the windows, and the green is what's left. The ventilative cooling and the economizer loads largely overlap. So when we use ventilative cooling, we essentially reduce the time that we're economizing. And a lot of data here, so I'm just going to go over some highlights and can share the rest with you via written form if you like. But basically what happens here's our respiratory aerosol removal. Now in this model, we have a MERV 13 filter. So the MERV 13 filters are really good. They remove about 77% of respiratory aerosols on a single pass. And so what we can see is kind of regardless of which system we're using, the respiratory aerosol removal is pretty decent. The bigger systems, like the cities with the bigger air handlers, right? We get more respiratory aerosol removal. The cities with the smaller ones, we get less. And so we essentially make that up with this system with portable air cleaner capacity. So the purple lines are the extra air changes we're getting from the portable air cleaner capacity. So the big deal with this system is maximum indoor PM 2.5 exposure. So for example, if we look at the gray bars outdoors, so if we look at like Stockton, San Francisco, Seattle, this is the average peak outdoor exposure for that year. And so you can see the outdoor is really high. Indoors, for example, in like Stockton or Seattle, we bring the maximum exposure down by like 10 to 25 micrograms per meter cubed. That's really significant. That's the difference between people ending up in the ER or not, right? So those types of changes, the magnitude of those changes are important for like the magnitude of the changes associated with a reduction in hospital admissions and ER visits for asthma exacerbation. If we are bringing in less outdoor air when there's high PM 2.5 outside, we're collecting less particulate matter on our filters, right? And so we also see with the IAQ energy controller a reduction in collection on the filter, and so that will mean an extension of filter lifetime. And finally, in terms of energy, the IAQ energy controller saves energy over a fixed ventilation rate, but uses slightly more energy than an economizer. And that makes sense because there's these hours of the year we would have been economizing, and instead here we prioritize health, right, by not economizing. And so like, for example, in like Los Angeles here, there's a little bit of take back on that cooling energy savings that we've essentially given up in favor of children's health. And I want to jump back to the MERV 8 filter. If I rerun these simulations, but I have a MERV 8 filter, this is the equivalent clean air flow for respiratory aerosol removals again. And you can see here that the differences now become much more significant in terms of the sort of the purple bars are now much bigger than the blue bars because of those small central air handlers. And now the difference between maximum PM 2.5 exposure with a MERV 8 filter is like off the charts, right? So like, for example, in Stockton on these worst air quality days, the amount of indoor PM 2.5 is just astronomical. And the IAQ energy controller sort of makes this manageable in a way it wouldn't otherwise be. So this is like shut down the school versus like we keep going, right? So conclusion, the energy savings, there's energy savings in most climates compared to fixed ventilation. The big deal is we reduce maximum exposure to PM 2.5. We also reduce exposure to respiratory aerosols, and these differences are more significant if you're using a lower filtration efficiency. All we need is a controllable outside air damper, some access to sensing, an internet connected portable air cleaner, and a programmable control system. We also need to be able to do demand control ventilation. We need to be able to track a CO2 set point. Historically, those algorithms don't work very well. We have demonstrated a proportional integral feedback algorithm for DCV that works extremely well in most building types, and that's published. And so I'll share the link to that as well. And then we've now taken this complete system and it's been operating for the last year in 2 classrooms in California's Central Valley. And my last slide here, I'll just show a quick diagram of that. Basically, we took a Trane building management energy system already existing. We added a internet connection. We used the existing internet connection to pull data from the AirNow network over the internet. So we don't have to add any PM 2.5 sensors. We just grab that data from the internet. That feeds into the control algorithm. We added a CO2 sensor that feeds into the control algorithm, and we adjust the existing outdoor air damper. We also added this internet connected portable air cleaner. And again, it's receiving all its commands over the internet and operating sort of seamlessly. And so that is it.
Thanks so much, Theresa. I really appreciate that. And I think we'll have a chance for some questions and discussions in a little bit. Let's go to our last speaker, but certainly not least, Paul Raftery. And he's at UC Berkeley's Center for the Built Environment. Paul, are you able to share your screen?
Sure, just give me one moment there.
Sure.
Here we go. All right. Can you guys see my screen okay there?
Yes, we can.
Great. Well, first of all, really enjoyed both of those talks by Michael and Theresa. That's fascinating research there. It's great to see. Now, I'm going to be talking today about something a little bit different, but again, very much focused on research that we've done with DUCs, with students, with the community colleges. I'm going to be focused in on how we can reduce emissions, carbon emissions in existing buildings, both quickly and cost effectively. My name is Paul Raftery. I work at the Center for the Built Environment at UC Berkeley. And all of the work that you're seeing today was the output of a large research project that was the culmination of many people's effort, graduate students and other staff here at UC Berkeley and at UC Davis, and some local engineering and consulting firms as well. Just very briefly, a little bit about CBE. We're an industry university collaborative research center, been around about 30 years, and we focus on technologies in the built environment, generally in kind of large commercial building applications, but a wide mix of things. And the work that we do is sponsored by a variety of different industry partners, as well as state and federal grants. And you can see kind of a mix of the partner firms there. It's a mix of kind of a variety of different stakeholders in the construction industry, architecture and engineering firms, as well as portfolio building owners and product manufacturers as well. So the project that I'm going to be talking about today was just wrapped up this summer, actually, and it was funded by the California Energy Commission. And its focus was really on identifying ways to address existing large buildings and reduce the amount of natural gas that they consume in an effort to cut emissions and cut costs. And we really focused in on the heating hot water systems in these buildings. So the hydronic heating systems, so the hot water that's used to heat the building more than heat the domestic hot water that's coming out of faucets or showers or whatever in the building. And the scope of this project was pretty broad. We wanted to dive into the performance of different components of these systems in both the lab and the field, gather and analyze data from hundreds of buildings nationwide, and then demonstrate how much emissions and how much natural gas you can actually reduce in real office buildings by performing some of these recommended set of measures that we're doing and measuring the results. So just to kind of kick things off and give some context here, because I know there's a broad mix of folks in the audience. This primarily focused in on the folks who are, building operators or facility managers. But this is just to give you a background on what we're talking about here. And what we're focusing in is ways to reduce natural gas waste in these buildings. And there's a lot of drivers for that in existing buildings. The first one is the actual boilers themselves don't operate as efficiently as many people would assume looking at nominal efficiency. These are usually older pieces of equipment, very oversized with poor capability to turn down to low output or low loads. And we did some early work that measured really poor efficiency of these units in the field, and we wanted to go out and see how prevalent of an issue that was. And that drives a lot of wasted gas consumption. Another one is that heating systems often run way too frequently in buildings, and they often run at temperatures that are very high. Anecdotally, we had seen that many buildings run their hot water system 24/7, 365 days a year, which is obviously wasting a lot. So we wanted to see how prevalent that was. And we also wanted to see how much of an impact that was having, right? So a lot of the time when folks analyze these systems, they just kind of minimize or entirely neglect the amount of energy it takes to keep all of that hot water piping hot inside the building. Even if you're not using any of it, it still wastes a little bit of energy. We wanted to be able to quantify that. And then lastly, we know that HVAC controls in buildings are really far from best practice, and it gets worse the further back in time you go. So when you focus on existing buildings and you take a 30-year-old building that hasn't had a really in-depth controls retrofit, there's a large opportunity there to improve efficiency by just fixing the controls and bring them up to best practice. And this drives a lot of unnecessary demand from heating, especially in summer months. And all of these measures kind of combine, all of these issues combine together and cascade together, right? So if you are running your heating system too often and you have little bit of load in there to maintain those distribution losses, then and your boiler plant is operating inefficiently, those combine together to waste a really large amount of gas. So we wanted to see how much we can save by correcting all of those issues as much as possible in some existing buildings. So I'll show you some of the results from this project. This is really just a snippet of the outputs of this project. All of these will be at a link that I'll share at the end of the slide deck, and I'll also post in the chat as well. Each one of these kind of has its own paper. We're just going to give you kind of like a highlight, basically. So the first is that issue of boiler efficiency. So we went out and measured a whole bunch of different boilers in existing buildings of different vintages. One is the LA Metro office building that you're seeing here. This is a 40,000 square foot office building built under about 20 years ago. And what we did is we installed metering to measure the input gas energy and the output hot water energy in this building. So we can tell how efficiently that boiler is converting natural gas into hot water delivered into the building. And you can see the results there on the image. The x-axis in the lower plot is the measured hot water load, or the output of the boiler. And then the y-axis is the percent efficiency. And the average efficiency of this unit over the course of the year was 50%. And the nominal efficiency of this unit is 80%. So an enormous opportunity there. And one of the primary reasons is it's oversized, it's old equipment, and it doesn't turn down well. But an interesting thing happened in this particular site. That boiler actually failed. During the middle of the study, And we only found out about it like a month later when we went back to download some more data. And at that point, the building owner had already replaced the boiler without like reaching out to us or anything. So they didn't like take into account any of the data that we were collecting for sizing it. And they put in a new unit. This is the brand new high turn down condensing boiler, but still quite oversized. This unit has a nominal efficiency of about 90%. And even with this brand new piece of equipment, the measured efficiency is only about 73%, again, because of an oversizing issue. So these sorts of results highlight that there's quite a bit more efficiency improvement we can get by focusing in on the plant and appropriately sizing that. And that's generally not being captured by engineering practice today. It's really not a core focus area because boiler capacity is cheap. So the driver for this really has to come from the facility owner or somebody else on the team to say like, no, we don't want a giant boiler. We'd rather have an appropriately sized boiler and take some tiny measure of risk that on the coldest day of the year, it'll be a degree or two cold so that we get that increase in efficiency. So we did that in some other buildings where we installed boilers and we really, really aggressively sized these boilers. They are half the size of the existing boiler plant. And we put in 2 of them and they have 20-to-1 turn down. So these pieces of equipment really are kind of pushing the boundaries of how you would size equipment. And even in these 2 buildings, they're slightly below the nominal efficiency compared to the manufacturer test data, because that test data is really set up in a way to be repeatable and steady state, but it doesn't really capture some of the losses that occur in real buildings. Like, for example, when you turn a boiler plant off at night and it cools down, you have to heat it back up again. There are some losses there. So even in this case, where we're really aggressively sizing, they're still performing below nominal efficiency. The building on the right there should be at about 95% average efficiency if you weight it by the low return temperatures here. But you can still see if you were to replace that 50% efficient boiler with a plant like this, you could almost halve the natural gas emissions in this building by really aggressively capturing that that energy waste, right? So there's lots more information on that in the paper on that topic. But I want to switch gears to one of the other scope aspects of this project, which was gathering data from hundreds of buildings nationwide to see how these systems are actually performing in reality rather than how we assume they perform based on kind of energy models that are in codes and things like that. So what we did is we reached out to hundreds of different contacts nationwide, all across the UC system and the CSUs, to gather basically trend data like you're seeing on the right-hand side. So this is time series data from the heating hot water system that shows things like the supply and return temperature, the measured load on the system, and kind of boiler performance characteristics like firing rate and things like that. And after that process of screening literally thousands of buildings, we cleaned up that data set down to about 250 buildings from 56 different organizations across the US. And because there's, you know, in some cases, 6 or 7 years worth of data for one building, it ends up being quite a huge data set. We have over 700 years worth of heating hot water system data. And we published a paper that has the insights that we gathered from that data set, but we also published the entire data set so that others can use it too. And there's lots of interesting things we found there, but I'll just highlight one, and that's that it's true that these hot water systems are operating way more frequently than are being currently assumed in most people's assessments of these systems. For the typical building in the data set, it operates over 80% of the hours of the year. Right. So for context, building operating from 6 a.m. to 6 p.m. Monday to Friday, that's only 36% of the hours of the year, right? This is more, almost twice what the typical kind of code compliance models are assuming these systems are operating. Another way of looking at this is 2/3 of the buildings have hot water systems that are operating more than 12 hours per day during the weekend when they're unoccupied, in the summer months when you're trying to cool the building, right? So this is a big problem, right? Or you can look at it as a big opportunity to reduce emissions very cost effectively, because essentially this is just a controls and a scheduling fix that almost any automation system can handle. And even in the cases where there's some minor repairs that need to happen to make it feasible to turn that hot water system off, the savings are quite large compared to the cost of that measure, especially when you consider alternative means of capturing savings of that magnitude. So the last element that I kind of mentioned I want to highlight here was that these systems have some distribution loss, heat loss in the system that isn't being accounted for in how we assess these systems today. And one of the reasons that isn't accounted for is because standards like the ASHRAE 90.1 standard say that piping losses shall not be modeled, right? And they're always assumed to be zero. But even in idealized conditions, there's still some heat loss through the insulation, right? And in almost every building I've ever seen, there's many sections of piping that look like this in the image you see up here. Exposed sections of piping around a valve or a fitting, or just poor installation, right? So what we wanted to do is go out and actually measure these losses. And that's what you're seeing here is the kind of supply water temperature of the hot water system on the x-axis, and then the actual losses normalized against the building floor area on the y-axis. And then these are 7 different buildings where we went in and took these measurements. Essentially, we kind of turned off the air handler, closed all of the valves to radiators or fan coils or VAV boxes, and just circulated hot water in the system and measured how much energy it took to keep that system at the normal temperature and flow that it operated at. And for some context, the average of these losses is about just a little bit less than half of average plug loads in office buildings. But this is almost entirely waste, right? There's no real benefit to this except on the most extreme of winter days. In the summer months when the system is operating, you're paying for it twice, both to heat it up, like heat up the hot water with your natural gas boiler, and then reject that heat with a chiller or a DX coil up at a rooftop somewhere. And again, because these systems are operating very, very many more hours than that they really should be, they're servicing these kind of distribution losses a large part of the time and operating the entire plant at really low loads, which is where boilers operate the least efficiently, right? So it's driving way more gas consumption than you would think for such a small load. So I did promise we'd go back and look at the actual real world impact of these. And we did that in this project. We demonstrated how much emissions you could save by fixing these issues. The 2 buildings that we focused in on were 2 large office buildings, both over 100,000 square feet here in the South Bay. And they're about 20 years old, a little bit less. So pretty representative of the existing building stock, maybe a bit newer than average, right? So this isn't even an extreme case. And they're entirely office buildings, so there's no, labs or any unusual loads in there. And they're about as typical as you can get. They have one non-condensing boiler up in the roof penthouse, a chilled water system serving 2 air handlers in each building, and roughly about 200 VAV zones with hot water reheat on the perimeter zones in each building. At a high level, the measures that we did were we replaced the existing boilers as part of an end-of-life redundancy project, and we sized really small, new, high turn-down condensing equipment in replacing those kind of large, oversized, non-condensing equipment. And then we also implemented best practice controls for the HVAC system following ASHRAE Guideline 36. And we did this everywhere, right? From the zones all the way up to the air handlers and the boilers. So this was not like a typical retro commissioning exercise where you only touch the boiler plant or you maybe fix the supply air temperature set points on the air handler. We went to every single zone in the building and corrected the set points and the controls and did that iteratively over a year to make sure everything was tuned correctly. So this was a much larger effort than is normally undertaken in a retro commissioning project. But we didn't actually have to replace the physical controller hardware. So we were able to do this without replacing all the actual hardware. So this is all just software changes on the building automation system, right? And combined, those 2 effects had this impact that you see here. On the x-axis, you have the average outdoor temperature each day, and on the y-axis, you have the measured natural gas consumption in therms per day. This is actually the PG&E meter bill data, so this is the entire building's gas use that day. The blue line is the pre-retrofit condition, and the yellow is the post-retrofit condition. And this is about a year's worth of data here. And what you're seeing is about 70% measured annual natural gas savings in this building. But we did it in another building, and exact same result, about 70% measured natural gas savings. And because this is the natural gas meter data for the building, this is a 70% scope 1 emissions reduction on site, which you can't achieve by almost any other means, right? We didn't electrify anything. We just leveraged an existing plant replacement, and we were able to reduce the scope 1 emissions by 70% in these two buildings. There are also HVAC electricity savings. So we saw about 20 to 25% fan energy savings and about 40% chilled water savings. And when you combine all those together, it's over $100,000 worth of avoided energy cost for these two buildings per year. So you can nearly pay a facilities engineer just to sit and watch and babysit these buildings. Not that we have to do that, they just work by themselves, but you could pay them to do this in more buildings, right? Based just on these energy cost savings alone. So what I really want to highlight, and if you only take away one thing from my talk today as an engineer, a facilities engineer or manager, is that there's way more potential to reduce emissions in existing buildings through efficiency measures than people think, right? We're not capturing these savings in the rush to electrify things. I fully agree that we need to electrify heating systems, but first, we need to fix the waste that's happening in buildings and then electrify, because that's where we'll get the most cost-effective savings, and we'll also get a larger overall emissions reduction from doing so. So if you're, working on buildings or you're managing people who are working on buildings, we have a design and retrofit guide that was one of the outputs of this project. And you can kind of screen very quickly for good candidates for some of these measures by looking for buildings that have any of these characteristics. If you got a single old non-condensing boiler or a boiler plant with poor turndown serving a building, that's a great candidate. If you look at the zone level and you see minimum airflow rates that are at or above 30% of the maximum flow rate, that's a really good indicator that there's a very large energy saving opportunity there, just through controls measures. On the heating plant side, if you see these heating systems that are running 24/7 because somebody 20 years ago heard about a leak in another building, but then ran the hot water system 24 hours a day, then there's also a good opportunity to reduce waste there. Same goes for the temperatures not resetting, especially in summer months. If you still have the same temperature water as you had in the winter, there's a lot of energy waste happening there. And that's true regardless of whether it's a district hot water system or steam system or a dedicated boiler plant in the building. There's still a lot of waste happening. Another way you can screen for this, which is one we did up at the Cal Poly Humboldt, is we took the gas bills for the building at the building level, filtered out all of the buildings that have like a lab or a cafeteria, and looked for those that have high summer gas bills. And we were able to identify a bunch of buildings just from the monthly gas bill data that have a lot of these issues and could be remedied. And then the last point that I'll try and drive home is that to achieve this, you really need to train and incentivize your building operators, because if they don't have the resources, the knowledge and the time to do this, it's almost impossible, right? This is not like an RCX project where you hire a consultant, they do some light touch controls work on the automation system, and then they walk away. This is a more iterative process. That's more involved, and it takes facilities engineer time and engagement to be able to facilitate that process. But the savings are very large, and they persist as well. So with that, I'll wrap up my talk. There's a QR code and that will direct you to the project website where all of these papers and data sets and guides are located. The link is also there, and I'll paste it into the chat as well. If you have any trouble finding something or have a question or anything, you have my email there as well. So with that, thank you very much.
Thank you, Paul. And yeah, it'd be great if you put the link in the chat, but just
Sure.
remember to send it to put it to everyone, not just the host and panelists. And then yes, just to be clear, I think we're recording and sharing these for folks.
Oh,
so
great.
you should be able to but it'd be great if you share the link. I'd like just to ask everybody to join me in showing some appreciation virtually for our three panelists, just for presenting. We'll open up for Q&A here, but thank you so much for putting together great presentations. And I hope you're as impressed as I am with the quality of that research, and also kind of the, just you've been able to distill down a lot of this work and your research in some really practical ways that we can save energy, reduce emissions, improve performance, that both impacts health, but also saves money on whether it's filters, refrigerant, fuel, across different HVAC systems, vehicles, boilers. I mean, it's just a great kind of collection. I realized that we had a diverse group of perspectives, and so I really appreciate that. Before we kind of open it up for questions, and I see, Tom, you've got one already. I wanted to ask, the theme of this, of course, is a living laboratory, and all of you had touched different campuses as part of your process for conducting this research. And so I'm wondering if you can share, about that process, what you might have learned from that engagement process during that effort that could inform either your future engagement efforts with campuses, and/or can inform others that are engaged in this living laboratory approach. So, Michael, maybe I'll start with you. If I see you nodding, so go ahead.
Absolutely.
Thanks.
I mean, it's a really interesting question. I mean, our sort of typical engagement has always been either through the energy management side, the efficiency, the purchasing process. But I think uniquely, we're starting to find that the non-energy benefits side of the equation has been an interesting entree into the campuses, and we're getting. I mean, it's a little bit of a challenging process, but we're finding that newer doors are opening to us through this process, and that incidentally we get large energy savings. But the pitch starts with a human factors issue, a health benefit, wellness benefit, visual quality benefit, something that starts first and then leads to oh, by the way, there's a large energy saving benefit. So I think that's been a unique experience for us particularly.
Great. Yeah, and I know you spent quite a bit of time engaging, the police department, the different departments on campus, right? So that manage those different fleet vehicles. So I want to before we kind of continue on, I want to hear if Theresa or Paul, you had anything to share on this.
So for the studies that I shared, both of them happened at school districts, and the reason we were essentially looking for the one school district we used just because they actually had excellent records of their refrigerant, which was just essentially luck, right? And the second is that we were looking specifically for a K through 12 type occupancy pattern for our study there. For air quality, the most challenging issue is that at a very high level, like at a superintendent and a board level, districts are very nervous to have researchers measuring any type of indoor air quality parameters because of the potential associated findings and then whatever risk they may perceive that has. And so that's just a huge hill to climb. And what I found is that when facility managers are really empowered and they have a lot of I guess autonomy at their district and ability to make decisions is generally where we're successful at being able to get those studies off the ground.
Thanks, Theresa. Paul, do you have any thoughts to share on this?
Yeah,
your
sure.
experience?
So I think we've always had great success working with students and engaging them and kind of teaching them about how these systems operate in real buildings. And that has largely only been possible because we've had campuses collaborate with us. And this project was no exception there. Maybe it might have been the outlier on the high side, because we were able to gather data from literally 50 different organizations. And while some of those were commercial entities and corporate entities, a large fraction of those organizations were California state institutions like, UC Davis or UC Berkeley or any of the CSUs. And even outside California, a large number of the other other data sets were from other universities and state colleges. So the ability to share data and information publicly without restraint is a huge benefit that we're only kind of beginning to leverage, and then have students look at that so they can learn more and go out into industry and really work on these systems, I think is something I see a huge advantage of.
Great. Thanks to all of you for sharing. And Paul, I think there was one follow-on question that Tom did add to the chat here, and it's specifically about kind of the multiple interventions that you included.
Sure.
Some of them was reducing or stopping the volume of heating hot water you circulated when there was no heating needed. So to reduce the waste heat loss in the distribution system. The question is, can you comment on what percentage is attributable to that intervention versus the other interventions that you kind of suggested?
That's a great question.
You used.
Yeah, so it's very difficult to separate these out, and I'll tell you why, because they're completely linked, right? If you have a very inefficient boiler plant because of low part load operation, because the boiler is operating at really low loads, and those loads are caused by the distribution system, by pumping water around the distribution system and losing a little bit out of heat, it's hard to say how much energy is saved from fixing the boiler and putting a low turn down boiler, and how much is saved from reducing the minimums. I can tell you that as a fraction of the heating load in a building, it ranged, I think that we looked at that across the data set, and that 1.5 watts per meter squared was about 11% of the annual heating load across the data set. So it's not a huge chunk, but we suspect that has an outsized impact on the natural gas consumption, because that 11% is driving your boiler plant to work at the absolute worst possible efficiency point, where sometimes it's operating at efficiencies of like 15 or 20%, right? So when you factor that into, you take that 11% and actually look at the gas use associated with it, it's much larger. And again, I think probably if you're looking at one measure to save the most energy, I think correcting the VAV minimum flow rates in existing buildings is probably the single most overlooked measure that has the highest potential there. We did some projects for ASHRAE that led to the codes being changed, both at ASHRAE at national level and also in Title 24. That looked at just that measure in isolation, and we saw HVAC savings of 20 or 30% just solely based on correcting the minimum airflow rates in zones. But because that was a code change that trickled through the codes maybe about 5 years ago or so, it means that the vast majority of the commercial building stock still exhibits this problem. Like it's gotten to the point where I walk into a building and the first thing I say is, "Can I see the zone minimum airflow rates? These are wrong. You can save more money than you could pay your facility engineer for 4 months of the year just to work on this and nothing else." And you'll get that savings every single year from now on. And it also improves occupant comfort. So touching on what Michael said there, sometimes we use that as a way to get in the door, because in that study, we also measured the improvement in occupant comfort from correcting the minimum airflow rates as well. And sometimes that's more of a kind of perceived benefit for whoever the decision maker is than the energy savings.
Yeah, and hence your point, training and incentivizing building operators is really one of the most important things you're suggesting.
It's
Eric,
a big barrier.
Yeah, Eric kind of brought up another question, and I think it's probably a longer philosophical discussion it might lead to, which we probably don't have time for, but I'll just flag it because it is an important one, which is he talks about kind of, as we think about even impressive efficiency that you can get from, say, changing out to smaller boilers, you run the risk of installing new fossil fuel-based equipment that may be in operation for many years, and that even though electrification isn't as efficient, at least currently, due to long equipment life, you might actually end up
For sure.
saving GHG emissions. So, but it's interesting because you could probably document that, and you probably do in the design retrofit guide, where you can kind of identify these VAV reductions without, that's not actually installing and lengthening, right? So I'm sure.
Yeah. So
part of it.
very briefly, we looked at that as part of the paper. I just didn't touch it in this study. That particular project, we installed these boilers 4 years ago. It was an end of life boiler replacement project that we just kind of hopped on the back of. I think if that building owner had the crystal ball and they hadn't already allocated the capital, they probably would have gone with air to water heat pumps even at that point. But you're completely correct. If you have the ability to partially or fully electrify when you're replacing those boilers, I think you should go ahead and do it. You'll get more of an emission saving. And we quantified that in the paper, both the benefit of like partially electrifying while keeping some gas boiler capacity, and also fully electrifying. But in existing buildings, there's a lot of challenges. And the larger the building, the more dense the urban context, the more challenges there are to fully electrifying in a way that actually yields a net emissions reduction. It's, you run into electrical capacity constraints and structural constraints and space constraints, and it becomes sometimes very challenging. So I think we still want to focus on efficiency as the first port of call, and then electrify as much as you possibly can after that. But like jumping straight into the electrification thing without doing efficiency, which is what we see a lot of happening, is not going to yield the best outcome, right?
Yeah,
I
really good
can paste
reminder.
that
Thanks.
paper in there as
That'd be
well,
wonderful.
specifically. Yeah.
And thanks, Paul and Ben. I think it's 2:30.
Yep, we're good. We'll just wait one more round of applause or virtual applause for our speakers. Thank you, Theresa, Michael, and Paul.